pause. There it is, recording.
Cool.
Here.
Can you enable screen sharing?
You don't have that. Ooh, wonderful.
Yeah.
Boom. Boom. Boom, boom. Any better?
Yes. Cool. Is everything okay?
I can see, yep, you and your screen, so I'm all set. I mute myself.
Cool. Perfect. Hi, everyone. So the topic of tonight is a review of hyperparameter optimization frameworks in Python. So it is kind of a mouthful, but we'll kind of break down the topics and really look around a little bit on like what is hyperparameter optimization, what are the concepts behind it, and how can we evaluate these different offerings that are on around in the open source market, basically. So the slides and code, you can find those in HackMD and GitHub. They should be in the meetup link. If not, I'd be grateful if we can post them in the chat for everyone to get, because they're kind of long. But let's get started.
Yeah, we'll do.
Okay, perfect. Thank you. And let's get started while that's going on. So first, a little bit about me. So my name is Alihan. I'm Turkish. I'm a data scientist in CKDelta and here in Dublin. Now CKDelta is a company that is a part of the Hutchison Group, which is also, so we're in collaboration with a lot of other companies such as 3, Superdrug, Watsons, and so on. So we are the data innovation hub of that whole group. So we get to work with the data of all of these organizations. It's quite an exciting one. Check us out over there if you're interested. I'm an ex-mechanical engineer, so I'm one of those people who actually transitioned from another job. It's not really relevant, but I like to mention it because I like to remember the times where I didn't know how to code. I'm, as Laurent has been saying a couple of times, it's my first time speaking in Python Ireland, and that is due to an amazing workshop that we did 2 months ago, I think, by this time. We had a professional trainer for full day training. We did a lot of different exercises. It was amazing. I had a couple of different trainings in the past, but this was by far the best, and it comes with its own opportunity to talk. So what more can you ask for? And I'd like to mention also that I was a swing dancer in before COVID times, and I can't dance anymore, so I just like to brag about it. All right. So what we'll talk about today is basically, first we'll talk about what is hyperparameter and what is its optimization. And then we'll talk about how to evaluate frameworks. So what are each components of an hyperparameter optimization framework. A couple of people mentioned that they are interested in Kaggle. So you really want to know about hyperparameter optimization if you're interested in Kaggle. It's like one of the main things. And then we'll evaluate a couple of frameworks that's basically mostly about scikit-opt, hyperopt, Optuna, and Raytune. I'll go into why I selected these ones in particular. It's just that some people might ask, like, why these 4 in particular? I'll also explain my thinking behind that. And then we'll finish with a conclusion. So what is hyperparameter optimization? So first of all, it is an amazing excuse to slack. It's just like, it is much better than if you ever had used any kind of compiling language. It is much better excuse because it takes so long generally to do it. The main reason behind it is like your hyperparameter optimization is kind of getting the architecture of your solution, of your machine learning solution right, of your each combination of your model right. So you're optimizing an optimization pipeline basically. And in that pipeline, searching through all of those combinations, if you just want to optimize for too many things, or if you don't take the right steps, it can just take too much time. So it can, but it's a really good thing to just say, hey, it's just optimizing. I'll let you know in 2 days. It's not unheard of when you're just trying to tackle the problem. But even before that, going one higher level, like what are parameters that are not hyper, basically. So what is a machine learning model? So machine learning model is basically mostly there are a bunch of matrices in the background. So your idea is to get your input data, do some kind of hopefully clever transformations to it, and get an output. So by the way, this GIF is from 3 Blue, 1 Brown. I have a couple of things that I didn't create here, and at the end of the presentation, there's a sources section there that you, if you're interested in any of them, you can look into in a little more detail. These transformations, each one of these transformations that you do to your input data, they have a bunch of different names. They're mostly called weights, but you can also call parameters. And these parameters are these elements of this model that you tweak during the training. So for example, over here in this GIF, these W's, they're basically your weights, and these A's would be your input data, and you would learn, or you would tweak these weights in order to get an output of your desire, basically, of what you'd like, or what you configured maybe. It's not always what you desire for. So these parameters are so that's the key message about this. Then what are the hyperparameters? So the hyperparameters are the arguments or the elements that you set before starting this tweaking, so this learning element, and they are basically being used to control the learning process. So here you can see just all the hyperparameters that exist in the XGBoost model. XGBoost is a gradient boosting model. It's a tree-based model. It works in a way of it fits your samples once, and based on how much error it did in the previous iterations, it kind of reweights your samples. It's a little more complex than that, but one of the important thing is it has 16 different parameters that you can tune here. And before you start your learning process, you have to, like some of them has like sensible defaults, but you have to give some kind of value to each and to some of these arguments before you start your process. So for example, you can choose something like this, which can look like I just chose a max depth of 5, learning rate of 0.01, estimators of 350, and a subsample of 0.7. Is this good? We don't know. And the point of hyperparameter optimization is to try this out with different parameters to find the best fit or the best possible problem for your current issue, best possible solution for your current problem. And basically, you would follow a couple of steps while going into this. So we're talking about an optimization here. So we have to think about a metric to optimize. So it would be, so for example, if it's a regression problem, you would use, you might use squared error, which basically says that, basically quantifies how far away from your target on average, and then keeps training the model in those kind of things. You would check if you would need stratification. So stratification is splitting your data into groups in a way that conserves the original distribution of subgroups in your data. So what this would be is, for example, it's one of the most common examples would be fraud. So you would have maybe 1%, maybe 1 in 1,000 of data of fraud in your data. So you have to stratify to make sure that you have some of the fraudulent examples in your hyperparameter optimization. And after you see if you need stratification, you have to find a suitable validation strategy, which generally is cross-validation. So cross-validation is basically fitting, dividing your data into k folds. This usually is called k number of folds. And you would, for example, if you choose 5, you would train your model into with the 4 of them, test it with 1, and then do it with the other ones and test with the other one until you tested all of your folds against each other. It's just to see if your model is consistent with different combinations of data. And another most important thing is to decide on an optimization budget. So what this means is how long can you bear to keep this optimization up for? Is it weeks? Do you need the answer in 10 minutes? Is that okay? So all of these answers are important because there's so many things that you can optimize for in your model. So in this example here, I chose a negative mean squared error because it's a regression model, and then I chose 5 cross-validation folds, so it will divide my data into 5. And I create an XGBoost model, and here's one of the most important things. So this is basically I tell this grid search cross-validation object here to try my model with all of the combinations of these. So it will try with 150 estimators and 4 depth, 5 depth, 6 depth, and then move on to 200 and then try it again and again and give me the best possible result from all of this. Now you can see like how this could be so expensive to do. So that's why we kind of need the frameworks. Here's a link of a great talk on choice of K in cross-validation from a Kaggle grandmaster called Jeremy Walters. This choice of K actually can mean a lot of things based on what you're trying to optimize. So it's a great talk, so I would really highly recommend to go through it if you're interested to learn more about these steps. And so what could be considered a hyperparameter? So we talked about these arguments, but is there other things that could be considered a hyperparameter? Well, since the question is here, the answer is kind of yes. You can basically consider the model type kind of hyperparameter. So you could try a multitude of different models and choose the ones that work best with your problems. You can even take the pre-processing steps. So how you reshape the data, how you impute the missing values in your data, how you smooth your targets, how do you get rid of your outlier handlings. You can try a combination of these different ways and choose the best one. You could even take the feature engineering part of all of this model pipeline and get this in, and then choose the one that works best. So what about, you could try different unsupervised pre-processing, you could try different row statistics, polynomial features, include and exclude different features. All of those can be in a hyperparameter optimization pipeline, basically. Now, as I've been talking about a lot of different things that you can do, but one of the important things here is hyperparameter optimization is not a replacement for explanatory data analysis. So explanatory data analysis and your domain knowledge about things is basically how you reduce what you're going to search for before. Like if you know that your data, some of the features are incredibly skewed, it's a nice idea to then go back and in your pre-processing maybe do some transformations that would reduce the skew. Or if you knew that in some places it is more likely to have more outliers, it would be it's better to focus on those places than basically searching for everything. So always do a suitable explanatory analysis before going into all of these. And now on to the frameworks. Now, how can they help? So one of the questions, of course, we've been talking about is the process takes too long. So for those, we'll talk about efficient searching methods. We'll talk about trial pruning. We'll talk about distributed training. And we'll talk about analyzing which of the hyperparameters are most important and analyzing these trials. And now we actually have so many different frameworks that live in all of the machine learning capabilities. There's integrating these frameworks with themselves are usually very important. So we'll talk about how they help in that. So let's start with efficient searching methods. Now, the question here is efficient compared to what? Before this, I kind of talked about this grid search method, where you have a bunch of predefined hyperparameters, and you search through them and try each and every one of them until you get a result. Another one that is a little more common is using random search. So random search is instead of just trying each and every one of those parameters, you would sample from some range and try them out for a predefined times. So let's say that you would just sample from there 20 times, and then you would get an output. Now, these are what you learn when you start hyperparameter optimization as in classes or in MOOCs and stuff. But of course, trying all of these hyperparameters on all of these values doesn't sound that good. Like, what if some of the hyperparameters are not as important? Or what if there's some values where you see more consistent, like higher, better results more consistently? So these search methods basically allow us to do that. So what is better here is basically sequentially narrowing down the search space. Now I will go over these processes and talk about how these work, but I will not show how these are done. But there's another walkthrough here that's in YouTube that is from Abhishek Thakur, a Forex Kaggle Grandmaster, one of the legends, that he goes through coding all of these and trying them out for a couple of different problems. So it might be useful to go through that if you're interested. Now, the first one is going through doing the Gaussian processes. It's a big word, Gaussian processes, but basically how it works is, let's say that the graph over here is our target, like our unknown but correct distribution of our variables. And this part over here is like we're trying to minimize our function, so we're actually looking for this. Now, all of these methods that I'm going to describe, they start by randomly sampling some search space. And let's see that we would sample from here, here, we would sample from, from here, here, and then maybe from here. And then what this function does is it goes through an estimation process and tries to find the maximum likelihood of the area where we will get the lowest loss, or like the best result from our distribution. So Gaussian processes is one of the oldest ways to do it. It works great, but its main drawback is that it takes a long time to fit these Gaussian models and predict the next value. So I think about 10 years ago, 10, 15 years ago, we got from Yoshua Bengio and a couple of people working with this, we got another algorithm called tree of parson estimators. It kind of simplifies the whole thing a little bit by splitting the whole search space. So let's say that these are all all of our sampled points from our hyperparameter. It kind of works by splitting the space in two as good observations and bad observations, and fitting maximum likelihood, fitting a density estimation for a density estimation model on these two groups. So that's why it's tree. So it splits the data first. So those are kind of a tree model way, and then does the estimation on these this distribution estimators, where it kind of goes on is like, where's the location where it's the highest likelihood for the good group, but lowest likelihood for the bad group. So it kind of gives the next estimation from there. Another one of the common ones is using genetic algorithms. So genetic algorithms works in a way where we would randomly sample from a search space again, and you would kind of work in a way that you would both iteratively sample from the areas that was a little more that had better values in an area, and do some random mutations along the way, which kind of works well, but it's really suited well to distributed training. We talked about pruning. So let's say that you for the best one. So pruning is about why would you wait if you already know your training is going well, going bad. So you would just have so after a couple of runs, the framework would get an estimation about how the training is going, and it would cut it before it goes too long, saving loads of time. Distributed training, of course, we all live in kind of the age of cloud for most of us. It would work in, you would just distribute your training along in the CPU. You could use Spark or MongoDB. It's like the most common ones, where you would train in, or you have some other ways of coordinating multiple machines, such as just randomly or asynchronously starting a couple of workers, referring them to a central database, and that database would have a table that contain the previous trials. So when one of those workers is doing the next optimization, it can get the trials from there and then predict the next best estimate going like this. Or of course, you can use a Docker or Kubernetes to start these asynchronously. You could also go through the, one thing that I really like is going through these hyperparameter importance things. So not all hyperparameters are created equally. So you would actually, some of them are much more important. So in here, like, you have some outputs from a model that I trained for the recently ended Jane Street Market problem in Kaggle. So in here, the one on the left, you can see that the model's performance really increases much more with learning rate than with the other parameter that controls the sparsity of the parameters in the model. Now, what this would tell us is, we've been at the start, we talked about understanding which parameters are more important by doing the exploratory data analysis. You could also understand what is more important by looking into graphs like this, just to see which ones affect your model more. So in this one, I just stopped optimizing for sparse weight after looking at this. I just chose a value, but I kept learning rate in going forward, basically. Also, integration to, We could, as I said, integrate to other frameworks. So one of my favorites is using MLflow. MLflow is another open source package that can collect some statistics from your runs, and it collects them in a neat way so that you don't have to log the results, the parameters of your runs manually. It can also save your models inside of those runs, so you can refer to them later if you need to. Since we talked about in the hyperparameter optimization, maybe doing it for 100 runs, it's really nice to have a framework that can collect all of these and then can give you an opportunity to basically refer to those runs later on. Now we'll go into our frameworks at last. But so let me talk about like criteria for inclusion, why I selected these four. Now, first of all, it needs to be open source. So I wanted to concentrate on those. I didn't want to concentrate on anything that is library specific. So Keras Tuner, Telos, they're kind of focused in certain areas. I didn't want it to be platform specific. So Polyaxon is a great one, but it's just for Kubernetes. It's like it has to be updated in the last 6 months. Spearmint was a great package, but it hasn't been touched in the last 2 years, so it's out of scope. I just wanted to be a little more high adoption. So Sherpa is another great package, but it has just about 300 GitHub stars. So I excluded that because of that. And I also wanted to draw a line between AutoML packages such as Teapot or Boruta and hyperparameter optimization. Well, mostly because AutoML packages have like a wider, let's say, a wider look. So hyperparameter optimization basically looks at only the space that you have given. And AutoML package actually can also propose you different approaches. It can propose you like a pre-processing method that you haven't used, or it can also propose like a different model that is not in your initial search space. So I wanted to draw a line here because then it gets a little bit blurry. So that's why we are left with those four. Now, I said that it is not, I wouldn't choose anything platform or framework specific, but Scikit-Optimize is a part of a Scikit-learn universe. And almost all of the models that you would use would have some kind of wrapper to scikit-learn. Even Keras has a function that you can wrap your neural network and it outputs it in a scikit-learn way. So that's why I wanted to include Scikit-Optimize. So Scikit-Optimize is a pretty simple, way. It is quite similar to what we've seen for the grid search before. So you would again have your parameters, and you would this time it has a different way of showing these declaring these search spaces. So when you say integer 200 to 500, every time that it goes through the one of these iterations, it would propose you something between 200 and 500, and it would try optimization for like that. But one of the drawbacks of using grid search, you would only search for the values that you would pre-declare. So if you say 100 and 200, it would only search for those. But what if it is in 175? So you kind of cover that ground with the help of these frameworks. And you can get some real numbers, other integers. You can make it choose through some categorical variables, basically. And this Bayes search cross-validation, it works pretty much similar to that grid search cross-validation that we did before, that we've seen before. And Scikit-Optimize has mostly two kind of search methods. It it implements Gaussian processes. As we've seen, there almost there's most of the other packages actually get their Gaussian processes from Scikit-Optimize too. So it's a great way to start doing on that. And there's a decision tree and gradient boosting tree based search method in it as well. As pruners and schedulers, it is a kind of a poor offering. It just has some stoppers that can detect whether your solution has converged, or if some of your trials basically stopped optimizing, so it can stop it early. So they are kind of preset and they're basic, but they're there and works fine. In terms of distributed training, it kind of only works in as distributing between your CPU cores, but it's pretty simple. You just need to declare this n jobs per argument, then it works like that. But it has also some great plots, some great visualization and analysis tools for you to analyze the outputs of your data. So this plot that you see here, it kind of shows you how does the average results that you got from your model changes with each one of those with the changes in the hyperparameter and the relationship between these hyperparameters too. So it's pretty useful. And it basically has no integration to other frameworks. It is kind of an older package. Now, one of the things that you will see as I go through the other packages is these are kind of ordered from older to newer. So there is, of course, the newer packages had time to learn from older ones' mistakes or their shortcomings. And when Scikit-Optimize and Hyperopt was basically developed, there was like, I think Scikit-Optimize is 10 years and Hyperopt is about 9 years old. So there is quite a big time gap in between them. So they're lacking in some of those features, but it doesn't really change how good their search methods are optimized. But as I said, the Scikit-Optimize is part of Scikit-Learn Extended. So anything that can work with Scikit-Learn can also work with Scikit-Optimize. Hyperopt is another great package. It's an older one. I really don't like its API, to be honest, but it is one of the first ones that actually implemented the tree of parse and estimators. It has some great things in there. Especially, it is amazing for distributed learning if you're using Spark. But after Scikit-Learn, we kind of move out of Scikit-Learn Extended. So now we actually have to develop our own cross-validation split. So this kind of now we get this k-fold object from a Scikit-Learn's model selection sub-package, and use that to split our data into k different folds, get their indices, and with these indices subset our data and fit our model into all of the in each of these folds. And we report the average average of our error each time. This one also works kind of similar to Scikit-Optimize. We declare our parameters and our parameter space, our parameter search space, and it does the magic for us under the hood. A couple of things that I really don't like about Hyperopt is it actually even if you're doing a log uniform search, you have to log your learning rates over here. Otherwise, it doesn't find the correct ones. I always forget it, and I kind of hate it. And one of the other things is it kind of doesn't work that well with notebooks if you're a fan of that. And every data scientist have to use it at one point. So it's kind of a drawback for the whole thing, in my opinion. As a search method, it basically offers tree of parse and estimators, an adaptive tree of parse and estimators, and random search. It does little, but what it does really well. So That's why it's on the list, basically. It's as I said, it's one of the earlier ones, so it doesn't really offer any kind of pruner or scheduler. That's, I think, another drawback for the HyperOpt. For distributed training, it is an amazing way of just using this Spark trials object, and it can almost automatically detect the already existing workers on Spark and start your distributed training there. I think this is the main reason why you would still use HyperOpt today. It's also because it literally offers nothing in the hyperparameter optimization space. I can see in their GitHub that they're planning for something, but there's nothing in their current release. And it has no integration in the package to other frameworks. I feel like I bash a little bit too much on HyperOpt in this, but I actually like the package, but it is kind of, its age kind of shows at this point. Optuna, I like Optuna quite a lot. It's what I use at work. It is like a more recent package. I think it came out around in 2018, 2019. It works in a similar way to HyperOpt, but it enhances some of these and adds new search methods. This doesn't have a default cross-validation loop, so we have to define ours again, as we did with HyperOpt. And one of the nice things that I do that is about Optuna is it kind of allows does this prediction of the next best hyperparameters inside of a function that gets this trial object, and what this allows is to conditional generation of hyperparameters if needed. So I found it like some other, like you can do it in HyperOpt and RayTune as well, but I found it easier in Optuna, where, for example, if you actually are sweeping through a lot of different models, you can basically say, generate these set of hyperparameters if you chose this model, and if you chose the other model, generate these other bunch of hyperparameters very easily. So it kind of makes a great general usage. And the rest is quite the same for, you create a study, you say which direction that you want to minimize, and start your optimization. It implements trio of Parson estimators, this CMAS, NSGA2, and ModP. These are all genetic algorithms. This is one, and they're nice, but they're nice to use. But I find myself always going back to trio of Parson estimators, because genetic algorithms, most of the time they do not support categorical variables in them. So you always have to use numeric ones. So I always going back to trio of Parson estimators, but if you have a solution like that in your hand, it's very useful. It offers quite a lot of pruners and schedulers. It offers a median scheduler. So these kind of think about, so it first starts, by, for example, for your first 10 iterations of the model, it learns like what is, it kind of records what were your individual values. And after a while, if any certain point of time, the model that you're training is less than a certain threshold, it would just stop training. So these are all different strategies that implement that. So it has quite a healthy amount of strategies in Optuna. In distributed training, before I talked about this asynchronous training, where you would start multiple machines and refer them to same database. That is basically what Optuna implements at the time, currently. But I saw that they're developing something for Spark as well, but it's not available in their current release. But Optuna has also an amazing selection of graphs for getting to hyperparameter importances. So it kind of evaluates which of the parameters were most important for your current implementation. So for this one, you can clearly see learning rate and booster was more important than an estimator's argument that I trained for here. And contrplot, this is quite similar to what we've seen in scikit-plot. And the slice plot is what I saw, what I shown before. That was from Optuna. In here, you can basically evaluate how does each individual hyperparameter interacts with the objective value, and how did that change through the trials. Like you can see this color bar, it denotes the trials. So you can basically see it, see what kind of different values that the hyperparameter optimization tried and what they were results as it was ongoing. It integrates out of the box with 16 different frameworks. Those include Keras, TensorFlow, PyTorch, MLflow, or scikit-learn. And you can basically get the implementation of Gaussian processes from scikit-opt and use that in Optuna as well. So that's a very useful thing to also do. To our last package. So Raytune. Raytune is a really interesting one. It was released in the last year. It kind of cheats because it doesn't implement any of the search methods, but it can basically integrate with any of the other open source and some of the even proprietary packages, and use their search methods in Raytune. Raytune is kind of like a member of a group of packages that focuses on distributed training, serving, and optimization. So it is a really interesting package. It's really, I found it really easy to use for a distributed package. Those are most of the time a nightmare to do, but Raytune kind of gets it almost right, I'd say. It was quite easy to start using it. Raytune is really likes to work with anything that with any kind of package or any kind of model that you can report the intermediate values for. So it is really useful if you're doing a cross validation, or if you're training a neural network in that sense. It works in a similar way to the other ones. You first declare your search space, and then tell the Raytune to start running it by passing these parameters, how many times to train for, what will be your metric, and what is your objective function, or so on. As I said, in the search method, it doesn't implement anything, but it can use anything else. You can use Optuna, SIGOpt, which is a proprietary package, Hyperopt, or Bayesian optimization, which is another great tool, another great package that is similar to scikit-opt that I chose to leave out. Pruners and schedulers. Now it implements very similar things to Optuna, but it has this one very interesting thing that's called population-based scheduling. It is really nice for distributed training if you're doing it. It kind of starts a lot of different trials at the same time, but along the way, after a while, it mutates, it's kind of cross breeds some of the best algorithms. So it kind of, during the hyperparameter optimization, it exchanges some of the best hyperparameters and keeps optimizing like that. So it's a very interesting thing that is based on a paper from DeepMind. It's a very interesting one to look for. I haven't had a chance to use it, but it's a great concept. Distributed training, as I said, Ray is kind of focused on distributed training, but it has one advantage over the other ones, that you can basically create a YAML file like you're seeing right now, where you would say, you would create a number of workers in I think it works in only AWS and GCP, if I'm not remembering wrong right now, and start training your optimization like this. It works quite well out of the box. And you can also, of course, run optimization parallelly in local as in with the other ones. The main thing that you would have to pass is you would control this concurrency limiters with an algorithm object like this. And with this algo object, you can also get which search method that you'd like to use, basically. Analysis, it's kind of an interesting one. You can, as being a distributed package, it kind of gets another shot. It takes another shortcut, and the outputs of your hyperparameter optimization, it uses TensorBoard to log them to a central location. So well, TensorBoard worked great most of the time, and it basically logs in similar visualizations that we've seen to Optuna. It was really interesting to see this, and I'm sure that more people will start doing this, given what a good product TensorBoard is. As being one of the newer products, it also integrates to a lot of different tools such as MLflow, Horovod, Docker, Kubernetes, and so on and so forth. One interesting addition there is Horovod. Now, RayTune doesn't natively integrate with Spark, but because it has a Horovod, Horovod is another distributed package manager from Uber, and it can you can use Horovod to use Ray in Spark. I know it's a lot of things to do, but if you want to do it, you can. That's the point. As a conclusion, like I'm not here to basically tell you which one to use or which one not to use, but I kind of wanted to go through what are the different offerings and how to analyze these differences between packages, because there's, of course, in data science there is now a lot of different packages that you can, libraries that you can use to do anything that you can imagine. But this was just my way of thinking when I'm going through a new package and see which one that I could use or which one's the best one that I could use right now. So on top of the ones that we talked about here, I added another one that's just rates these packages on top of their simplicity. Well, this is on internet. I'm sure I'm not going to get any backlash over this or any angry messages from the developers. I kind of rated CKDelta as like in terms of like how are the choices that you have for your search methods, for your pruning, for your distributed optimization, for doing your trial analysis, or doing your integration. For me, on average, as I said, I use Optuna. I find that really easy to use and user-friendly. One of the other reasons why I gave Hyperopt such a low, let's say I have such low regard for it, its documentation is really not out there. It's hard to find any examples for it. But for all the other ones, their documentation is quite good. But CKDelta, it's quite easy to use. You can use it with anything scikit-learn. Hyperopt, a little bit less, as I spoke. Optuna, quite easy to use. RayTune, it is quite easy to use, but it's still about distributed training, and it comes with its downsides. So that is my evaluation and a review of the current things. So thank you for joining. You can find me in any of these, and you can find my sources for the things that I didn't prepare over here. And if you have any questions, now is the time.
Okay.
Don't be shy. There is the Q&A. Oh, I see one. Question: when would you recommend to use AutoML or one of those?
So I would kind of use it if I don't know enough about the problem or if, for example, if you're working on a problem where there is no domain knowledge that you can go for, or you can go for and you just want to limit your choices. So AutoML, I basically use it to get an initial understanding about what kind of seams work and start working from there on. Another good use for it is if you have too many problems on your hand that you want to, that needs attention. In that case, using AutoML for some of those problems, and for any of those, if you're within range of your expected values, if you have one of those with your client or with your supervisor, if you get there, okay, just stop focusing on that and do something else, basically. Does that answer the question?
It's the kind to create more questions, but Fernando seems happy with your answer, so that's that's the best. Yeah, I think this is an impressive display of experience and feedback. So not so sure it will bring so many questions, but please feel free. We still have a few moments. So
are you okay there? You look like you're in a blackout. Is the electricity gone or?
Ooh.